Okay, later we have a quarter of an hour for walking a bit, but now let's resume our class. Now we have to talk about graph isomorphism, meaning that two graphs are identical means they are exactly the same thing, not that they look the same, but they are exactly the same thing, meaning same vertices, same edges, and same function, okay, same incidence function, the same object. You might have two different drawings, as we have already seen, two different diagrams of the same graph, but meaning identical means identical in the three parts of it: vertices, edges, and incidence function. Now we have a different type of connection between graphs, which is isomorphism, which is very important. Isomorphisms are very important throughout mathematics, okay? In particular in algebra, in linear algebra, you have seen the isomorphism between vector spaces, for instance, and we'll have here isomorphism between two graphs. Now, I try to let you understand this idea by a rather silly example. Not far from here, in the eastern part of this region, Romagna, we have two particular villages, and they have funny names, but they do exist. One is called Premilcuore, and another one is called Dovadola. Okay? Now, assume one thing which is not true, but who cares? There are so few people in those two villages that we can also say wrong things. But imagine that the committees, the civic committees of the two villages have little fantasy, and they have given names to the streets and squares of their villages in the same way. As you would find in almost every Italian town, you have Piazza Roma in Dovadola and Piazza Roma in Premilcuore. And you have Via Mazzini in Dovadola, Via Mazzini in Premilcuore. Via Garibaldi in Dovadola, Via Garibaldi in Premilcuore. Piazza Italia in Dovadola, Piazza Italia in Premilcuore. Okay? Now, you have exactly the same names for the squares and the same names for these streets in the two villages. Do you think that having a map of Premilcuore, you might go through the streets and find your way in Dovadola or not? No. Sure not. It's not enough to have a bijection, vertices, edges. Why? You might have that Via Mazzini in Dovadola connects Piazza Roma with Piazza Italia, whereas Via Mazzini, a street with the same name, does connect Piazza Emilia with Piazza, I don't know which other name, okay? So the street with the same name does not connect the same squares as in the other place, okay? So it's not enough to have bijection, but you also must have the same incidence. The incidence is the one which says, to this street I associate the pair of the two squares which the street connects, okay? And so you must have that you need also that. And it is exactly what you do when you try to walk through a town by using a map. Just think of having a little cousin, okay, of 4 years, or maybe 3, let's see, because now 4-year children are smart enough, okay? And he says, cousin, or uncle, I want to go from here to Piazza Maggiore, okay? And you take a map. He or she would say, are you silly, uncle? We should look from the window to see our way from here to Piazza Maggiore, okay? Why are you looking at a piece of paper? We know why. because we are looking at a graph having edges made of ink between squares or crossings made of ink, and we are trusting that there is what we are going to call an isomorphism between this graph and the graph made of physical squares and physical streets, okay? And so you plan your way from here to Piazza Maggiore on the paper, trusting that it represents a way actually that you can walk. Do you see what I mean? You are using what we are going to call an isomorphism, and you don't need only a correspondence of the name of the street on the paper and the name of the street in the town, but also the fact that the incidences are preserved. So if you have the map of the Vadola, you cannot walk through Pernicore and conversely. All right? And so let's see this notion. The notion of isomorphism between two graphs, which essentially is that you can draw diagrams of both graphs in the same way as we had before. Do you remember? We had here a drawing of graph G on the left, a drawing of graph H on the right, but then you discovered that also graph G could be depicted by a diagram like this, and you see that this diagram corresponds exactly to the diagram of graph H, okay? And so this reveals what? That you have this, you have a pair of mappings, vertices of G, vertices of H, a bijection between the vertices of G and the vertices of H, and the bijection, this is called the letter theta, Greek letter theta, and this is Greek letter phi, and a bijection between edges of G and the edges of H, but with a condition. The condition is here, that if you have that the pair of vertices in G corresponding to each edge E are U and V, then if you take the corresponding edge in H, phi of E, this must be incident to not any two vertices, but exactly to the vertices corresponding through theta to U and V. Theta of U, theta of V. Okay? So, what happens always, what did happen in isomorphism of vector spaces? You have a vector space V and vector space W, and then you have a linear transformation T. Okay? What do you need? That if you sum two vectors in V and then go through T to the other vector space, or if you transform the two vectors and you are already in W and there you make your sum, then you must get the same answer. Okay? If you multiply vector, vector V by a number 3, okay, and then transform, you get the same as transforming the vector and then multiplying by 3. This is a linear transformation. If it is bijective, you have an isomorphism, which means this vector space is a complete, gives you the possibility of a complete simulation of vector space V. Whatever you are interested in vector space V can be computed and observed in vector space W. This is the reason why we make computations in vector spaces through n-tuples of numbers, okay? Just because you have an isomorphism which takes a vector to its n-tuple of components, all right? And so you make computations with matrices in linear algebra, because all which is a vector space of finite dimension on the reals can be replicated in the reals themselves, okay, in multiples of reals. And so emulation, simulation, complete simulation of one thing with another. Same thing here. You have the places, the crossings, the squares in the town, and you have their corresponding ones on the paper. And so you simulate the town on the paper. You see what I mean? You see, you have a simulation of the town in the paper. And so you can plan your way on the paper and then use it on the real streets. And so isomorphism is the core of all possible simulations in mathematics. In graph theory, this means if you have that an edge connects two vertices, then the corresponding edge must connect the corresponding vertices. If you don't have this, it's not enough to have two bijections. You don't have an isomorphism. You cannot simulate one vertex with the other. All right? And in the, you can check that. I don't go now back to the original graphs that we had, G and H at the beginning. But if you copy them and check, you will see that actually if you take these two bijections, theta from vertices V1, V2, and so on, to vertices Y, X, and so on, and phi from E1 to H, E2 to G, and so on, then you can check that actually you have this condition, okay? Psi H of phi of E equals theta of V, whenever you have that psi of G, psi sub G of E is equal to UV, okay? They have the same structure, so you can this is important in simulations. Now, again, terminology. A complete graph is a simple graph in which each pair of distinct vertices is joined by an edge. Okay? So, when all the combinations 2 by 2 are actually combinations which are effective in the graph, meaning that there is an edge between these two. This is the complete graph. Okay, and this is the current notation. K sub n means the complete graph on n vertices. Okay, an empty graph is one graph which has some vertices but does not have any edges. So it does not mean nothing. It means there are some vertices but no edges. This is an empty graph. Now a very important notion, bipartite graph. And I'm sorry, I must say that this very, very simple notion of bipartite graph has been the source of rejecting many experiments before. Please, pay attention. This theory, this subject, is very easy, but it's not trivial, it's not stupid, it's not silly. And so you must know things very well. Okay? And they appear to be very easy, okay, but keep an eye on them. Pay attention. What is a bipartite graph? It means that it is a graph such that you can subdivide the vertex set into two disjoint parts. So you can subdivide into two so that each edge connects one vertex of set A with one vertex of set B. And so no two vertices of set A are adjacent, as they are called, are joined together. No two vertices of set B are adjacent, are connected to each other. Is that clear? Thank you. Oh, please stop me whenever you have a doubt. Thank you very much. Okay. The important thing is that you can take the vertex set and subdivide it into families, let's say, okay? Family A and family B, so that each edge connects one of family A with one of family B. All right, so otherwise said, no edge connects together two of family A, no edge connects two of family B. Okay, so we can see, for instance, that graph on the right, which is called K33, and it's rather easy, with this drawing, it's rather easy to see that it's bipartite, because we have it physically, and so drawn like this, you see very easily that you don't have any edge between two vertices of family A, no edge between two vertices of family B, and the edges are all between one of A and one of B. This is also what is called the complete bipartite graph with 3 and 3 vertices, K3, in the sense that it has 3 vertices in family A, 3 vertices in family B, and it has all possible connections, all possible edges between vertices of family A with vertices of family B, okay? And you can have also quite a lot of situations in which you have a bipartite graph, when you have relations which are between something which is of two different types, which can be in family A you have teachers, in family B you have different classes, for instance, and you have the teacher which teaches two different classes, and also a class which is taught by different teachers, okay? And you don't have that the class teaches a class or a teacher teaches a teacher, okay? Or many other situations like this in which you have a relation between different sets, and they are very well depicted by bipartite graphs. We'll have many things to say about bipartite graphs throughout. A complete bipartite graph is a simple bipartite graph in which every vertex in which you have bipartition x, y of the vertex set, in which each vertex of x is joined to each vertex of y. And if you have m vertices in x, n vertices in y, those two bars mean number of objects. Cardinality is called cardinality of x, meaning the number of elements of x is m, the number of elements in x is m, the number of elements in y is n. Okay. Okay. You can have quite a lot of different types of graphs in Appendix 3, but it's not our business. And find an isomorphism between the graphs G and H of examples 1 and 2 different from the one given. Please try that. Please try to see whether you can find a different bijection vertex-vertex and a different bijection edge-edge between the two graphs, so that anyway incidence is preserved. Okay? Please try that. Now there are a couple of exercises which are very interesting in my opinion. And there is this which is very, very interesting. But before, let's stick for a moment to these pictures, and this will be part, a small part of an exercise listed later, okay? Can you see that it is bipartite? I say, it is bipartite, believe me, for the moment. And now, can you show that it is bipartite? You can also come here, okay? I'll reproduce here. Okay, give names. So, we can color vertices with different colors if they are in X or in Y. Okay? Suggestions. Or if somebody wants to come here, please, come on.
So we start with
Directly on the graph.
Okay. So we start with point of A, then
Color it.
okay. Point A, then any point connected to the A is belongs to B side, which is E and B point.
And so you can already.
Yes.
No, do it with.
Now we can delete. Then we can start with the E point.
And evidently, what
Yes.
is connected with D cannot be pink. It must be blue. So.
Yes. And so here is. Yeah.
Okay. And you can add them.
So we can start again with the C point, which is
Correct.
yes. And start here.
And you're done.
Yes.
Thank you very much. Sorry. Yes. All right. Perfect. Okay. So please observe. It's not that they are physically in different areas. That's no meaning. They are mixed all together. The important thing is the definition. Okay. And so I have had quite a lot, unfortunately, quite a lot of people which I had to say, please, the exam is over. You are not. You are rejected. Why? Because they said, okay, this is bipartite, and they put the bipartition like this on X and this on Y. No, it's not. You must follow the definition. Must follow the definition. Everything which is in the terms of mathematics is in definitions of the terms. Okay? And so this is the correct bipartition. Very well. Any questions about this? Don't be shy. Now you can make mistakes. Please don't make the mistakes at the exam. So if you have a doubt, I can understand the doubt, and I explain. If you have a doubt, please tell me. Why is Why is this division wrong? This is something which has been said to me quite a lot of times. Why is it wrong? Is that clear for everybody? If for somebody it's not clear, don't be shy. We are starting. It's the first lesson. Stop me and ask me, okay? No, it's clear to everybody. Tell me.
Can you repeat it?
Of course, sure, thank you. You must stick to the definition. So it's not just that you divide into two pieces, okay?
How the coordinate, did you write the coordinates and it's equal to A and C, how we write the coordinate?
The right one, you mean? He did it in a careful way. Start from A. He had color blue in his hand, and so he colored it blue. Okay? And now, whatever is adjacent to A must be pink. And so he started what is connected to A, adjacent to A. D, E, and B. And so he colored that pink. Maybe, if it's not bipartite, sooner or later he gets into troubles. Okay? He might get into troubles. But he did not. Now he has A, B, D, and E in the other. Now he takes one of the pink ones, D. So what is connected to D must be blue, if it is bipartite. This was already there, all right, and then he colored H and C. Okay? Now, again, what is connected to C, which is blue, must be pink. C, all right. And you had already B. There you might find troubles. If it were already blue, then you're done. It's not bipartite, okay? But it's pink. He was lucky, so to say, and it was already pink, and he had to put pink also here, and now you were left with this, which was connected to only pink, and so he could be colored blue. All right, let's take this, for instance, very simple. I try, and I don't succeed. I start from this, and it's blue. And then I say, okay, then these two must be pink. All right? All right. And so since this is pink, this must be blue, but this should be what? It's connected to a blue on the side, on one side with a pink on the other side, and then, I'm sorry, you should use, but you don't have a tripartite, you would have a bipartite, so this is not bipartite. There is no way of subdividing the set A, B, C, D, E into two subset X and Y, so that each edge of these edges connects something in X with something in Y. You get into troubles here, okay? He did not get into troubles, and so he has the bipartition. What is wrong with the answer I got so many times? This is one set and this is one set. What is wrong? That you have an edge AB, so connecting two vertices of X, and this is not allowed by the definition. The definition says that each edge connects something, a vertex in X with a vertex in Y. And here immediately you have an edge connecting two vertices in X. And so that's wrong because it does not respect the definition. Has it been clear? Okay. But I know a terrible thing. A spell, you know what a spell is? A magic, a bad magic. You understand everything up to here. Here, things are a little bit less clear. When you're downstairs and out, you don't remember a thing, and you say, what was it? Okay, I know it, and I can explain it again. Okay? Don't be shy. All right. Now, the exercises.
Sir, I have a question.
Oh, good. Tell me.
Can we assume that all the vertices have to be in even number for it to be bipartite?
No, not necessarily. Look at this. Okay, so you can have, this is called K32. for instance, you don't have necessarily that. Okay. Good. You had a conjecture, we have a counterexample. Remember this, we have two types of things which might happen when you try to prove or disprove something. You might have that you can prove something and you must prove it in a very general way, saying I take any graph and so and so. Later we have something like this with cubes, of which this is an easy example. And you must make a very general, very abstract reasoning. Or you might disprove something which has been said, like in this case. Your fellow student tried, maybe a bipartite graph must have an even number of vertices. Then for saying that's not true, the only reasonable thing to do is to find a counterexample. So something which is bipartite but does not respect what she thought it could be. Okay? Different ways of approaching a problem, trying to prove with a general reasoning, try to disprove with a particular example called a counterexample. Okay? What about this? Again, oh, sorry. What about the previous problem that our Chinese friend solved? It would have been easy to solve if we had already the notion of complete graph. Okay, if you have a complete graph, it is sure that that has exactly d over 2 edges. Okay, every vertex is connected with every vertex, and if you have a simple graph with those vertices, it must have either that set of edges or a smaller set of edges. So if you already knew the notion of complete graph, it would have been easier to solve that problem. Now there is a similar thing. There is a notion which will come later, not immediately later, a bit later, which would help you to solve this problem. How can we think that prove that these two graphs are not isomorphic? You know, proving non-existence is not easy. It is a nice thing that you have in mathematics. If I want to show you that two graphs are isomorphic, what can I do? One possibility is I produce an isomorphism, meaning a bijection theta between the vertices, a bijection phi between the edges, and I check that the incidence is respected. Okay? So, to show that some two are isomorphic, here they are, and I show you an isomorphism. To show that these two are non-isomorphic, it's a much harder thing if you don't have ideas. I mean, you can use brute force, but brute force is not an easy thing to do. How many vertices do we have? 5. Meaning that if you take all possible bijections between the vertices on the left with the vertices on the right, you have 5 factorial possibilities. Okay? And for each of these 5 factorial possibilities, you have how many? 1, 2, 3, 4, 5, 6, 7, 8 edges, and so you have 8 factorial bijections between edges on one side and edges on the other side. So 5 factorials times 8 factorials. Okay, I know that you have computers, but don't let them make you become lazy. Okay, we can solve without that extremely brute force procedure of saying, okay, I'll try, they are finite objects, and so I'll try all of them, and then I see whether it's possible, and I see the first couple of bijections does not work, the second does not work, the 1 million does not work. Okay, so they are not isomorphic because I have tried all possibilities. Now, we can do better. For instance, I said that we have 8 factorial bijections between the edges on the left and edges on the right. Are there some constraints that we have? Is there, by the way, some edge which has to go to a particular edge on the other side, if we have to preserve the incidence? Okay, I see one particular edge which has no possibilities other than a particular one. I see one on the left which has to go to a very particular one on the right.
That is what I was saying. Right. Just because we are seeing them and we are comparing, is it enough to detect an answer?
If you detect an answer, you show that they are isomorphic. But here you have to prove that they are not isomorphic, meaning the authors know that they are not isomorphic. And so, in principle, you should try all 5 factorial bijections, vertices on the left with vertices on the right, and all 8 factorial bijections, edges on the left, edges on the right. But is it really 8 factorial, or is there on the left a particular edge which has to go to a particular edge on the right if we want to preserve incidence? Come on, bad ideas, wrong ideas. We want to laugh a bit. It's late in the afternoon. It is even Monday, and so we are tired from all the holidays, and so the loop on the left has to go to the loop on the right, because we have on the left a particular edge which connects a vertex with itself. It has to go on the right to an edge connecting a vertex to itself. Correct? If we want to preserve the adjacency, the incidence. Okay? If you have an edge on the left which has the same answer, then you must have, by the rule that we saw before, that you must have an edge connecting a vertex with itself. You must have this, okay? If you have psi of g of e equal uv. Now, what about a loop? A loop is connecting u with u, all right? Let's call u that vertex. So you must have, you have psi g of e equals u, okay? Then, if you have an isomorphism, what happens is that phi of e, so the corresponding edge on the right, must be what? Theta of u again. So the same vertex again. And the only possibility is that you have that this edge goes to this edge. So we have already restricted quite a lot. I saw that we had 8 factorial possible bijections between edges and edges. It's not like that, because loop must go to loop, and so you already have 7 factorial. It's not a big progress, but still it is some progress. Now, are there other edges which must go to some particular edges?
Multiple edges.
Very good. These multiple edges must go to these multiple edges, and we have 2 possibilities, okay? We might have a flip, okay? It's not unique that possibility, meaning the external one can be correspond to the external one, or the external one here could correspond to an internal one here. All right, but of course these two must correspond to these two. Okay, and now we can discover that they are not isomorphic. Why? If we have that these two edges correspond to these two edges, what can we say about the vertices? That these two vertices must correspond to these two vertices. I don't know how. Maybe this way or this way. Okay? But surely, if you give names to these two vertices and names to these two, let's call them A and B and this U and V, either you have A to U and B to V, or A to V and B to U. Okay? Anyway, surely these two must correspond in some way to these two. All right? Also, this vertex, if the loop must go to the loop, also this vertex must go to this vertex. Again, what we have, I said five factorial permutations, bijections. It's not true, because that vertex has to be must correspond to that vertex. And so you already have 4 factorial, but you have something even more direct for proving. What do we know?
There is a connection between the loop and
Exactly. You have a connection. Let's give names. Giving names always helps. Let me give names just to the vertices, not to write too many things. A, B, C, D, E. And here, U, V, W, X, Y. Okay? Now, what you have is that surely the, let's use the theta of D must be W. Do you agree? You don't agree? Somebody does not know why I'm saying this? Since the loop must go to the loop, also the vertex where the loop is must go to the vertex where the loop is. So surely theta of D must be W. All right? And then what do you have here? 2 possibilities. Possibility 1, it is that A goes to that theta of A equals Y, theta of E equals U, or 2, theta of A equals U and theta of E equals Y. Do you agree? Meaning, since these 2 multiple edges must go to the multiple edges in some way, also these 2 vertices in some way must go to these 2 vertices. All right? So one possibility is this, and the other possibility is this flipped over. Okay?
One of the edges missing. one of the edge is missing.
Is?
Missing.
No. Oh, sorry. Oh, yeah, sure. No, it doesn't. Okay. Correct. Now it's okay. But what do we have? Let's look here. This possibility. In this case, you have E connected with the D. Okay? And so you must have that theta of E should be connected with theta of D. Is that true? No, because U and W are not connected. Okay? Do you follow me? You don't? Okay. Other possibility given by the fact that multiple edges must go to multiple edges, you might have that theta of E is Y. But also Y is not connected to W, whereas E is connected to D. So this incidence is not preserved here. And so there is no possible bijection of vertices, bijection of edges, which respects the incidence. You're not convinced? Okay. Let's take one thing by one. We have some constraints given by the particular things which we have. First constraint, loop to loop. Do you agree then that the only possibility for D is to go to W? So this is sure, okay? Now, what can we say about A and D?
That it has to be similar as B and Y. U and Y.
U and Y. I don't know in which order. Which it might be A to Y, E to U, first possibility. It might be the other way around, A to U and E to Y. Okay? Do you see other possibilities? Out of the thing that multiple edges must go to multiple edges, can you have other possibilities?
Okay, no.
No. Okay, but here, E and D, they have an edge in common, okay? And so you must have that theta of E and theta of D must have an edge in common here. But first possibility, what is theta of E? It's U, okay? U, is it connected with to W here? No. So this is not correct. Let's see the other possibility, that theta of E is Y. But Y is connected with, is joined to W? No. So also this possibility is not true. And this means there is no possibility to have. You have quite a lot of bijections, vertex to vertex, edge to edge, but none of them respects the incidence. All right? Do you see what did I tell you? These are very simple things. Simple does not mean easy. Simple does not mean easy. You must be very well convinced of all this. Okay? If you are not, please ask again. Please ask again. Okay? All right. So now I give you 15 minutes. It's 51. So I'll start at 6, meaning 6 minutes past 5. Okay? So you can have a moment, relax before the next exercise.